Hi everyone. In this video, we are going to discuss about previous examination question in the year December 2017, and this is the example of the Smith chart. And the question is a lossless transmission line of electrical length 0.4 lambda is terminated with a complex load impedance as shown in the figure below. Find the following using Smith chart. First bit, determine the reflection coefficient at the load. Second bit, the standing wave ratio on the line. And third bit, the reflection coefficient at the input of the line. And fourth bit is the input impedance to the line. And this is the question. Now coming to the solution. And this is the given figure. In the given figure, the characteristic impedance Z0 is 50 ohms and the load impedance ZL is equal 60 plus J 50 ohms and the length of the transmission line is 0.4 lambda. So now coming to the solution, given that the characteristic impedance Z0 is equal 50 ohms, load impedance Z suffix L is equal 60 plus J 50 ohms and length of the transmission line L is equal 0.4 lambda. And first determine the normalized load impedance. Step 1, determine normalized load impedance. Find the normalized load impedance. So we know that the definition of normalized load impedance is given by or defined as Z suffix small r is equal Z suffix L by Z0, where Z suffix L is the load impedance, Z0 is the characteristic impedance, Z suffix small r is the normalized load impedance. Here substitute ZL and Z0 values. ZL is 60 plus J 50 ohms divided by Z0 is 50 ohms. So that is equal 60 divided by 50, 60 divided by 50, 1.2, 1.2 plus J 50 divided by 51. And this is the value of the normalized load impedance. So here in this equation, the normalized load impedance is a complex quantity. It has the real part and imaginary part, and 1.2 is the real part of the normalized load impedance and 1 is the imaginary part of the normalized load impedance. So R is equal to 1.2 is the real part, R is equal to 1.2 constant circle and X is the reactance which is the imaginary part, X is equal to 1 constant circle. And this is the figure of the Smith chart. See in this Smith chart, this is the horizontal axis or the real axis and these are the different R is equal to constant circle and above the horizontal axis it has positive reactance values and below the horizontal axis it has negative reactance values. In this Smith chart, mark R is equal to 1 constant circle and this is R is equal to 1 constant circle and this is 1.2 constant circle, 1.2 constant circle and X is equal to 1 reactance circle and this is X is equal to 1 reactance circle. Here and this is the center point 1 comma 0 point and this is the origin, this is the center point. So this center point is considered as O and after that using scale connect point O and point P, connect point O and point P. That using compass, O as the center point and OP as the radius, draw VSWR circle. Draw the VSWR circle. And this is VSWR circle. This is voltage is standing wave ratio circle or constant S circle. This VSWR circle intersects horizontal axis. This is the horizontal axis. So to the right of this Smith chart, this VSWR intersects the horizontal axis. That intersection point is considered as a point M, and this is the intersection point. So this intersection point is considered as point M. From center to the point M, this distance is VSWR value. And this is 1, 2, and this is 3. So 2.2, 2.4, 2.6, and 2.5. So the VSWR value is from the figure, the VSWR value is 2.5. VSWR value is 2.5. Extend OP line. This extended line is cut to the outer rim of the Smith chart, and this is the outer rim of the Smith chart, and this is the crossing point on the Smith chart. So this crossing point is considered as a point P. This crossing point on the outer rim circle is considered as point P dash. P dash. So this is 0.17 and this is 0.18, and approximately this value is 0.174 lambda. 0.174 lambda. So next, determine magnitude of the reflection coefficient and phase angle of the reflection coefficient. So how to calculate the magnitude of the reflection coefficient? The magnitude of the reflection coefficient is determined as, and this OP value, and OP is the radius of the VSWR value. This OP is equal magnitude of the reflection coefficient, in reflection coefficient scale. This is the reflection coefficient scale. So in this reflection coefficient plane, and this is the center point, and this is the center point. Okay, the magnitude of the reflection coefficient is equal OP. Okay, the OP value already measured using compass. So the magnitude of the reflection coefficient is equal to OP. And from center to this is the magnitude of the reflection coefficient. So what is this value? Approximately the magnitude of the reflection coefficient, this value, and this is 0.4 and this is 0.5 and 0.45, 0.25. Approximately the magnitude of the reflection coefficient value is 0.425, and this is the magnitude of the reflection coefficient. Next measure, determine phase angle of the reflection coefficient. This OP line is extended. This line is cut to the inner circular rim of the Smith chart, and this is the outer rim of the Smith chart, and this is the inner rim of the Smith chart. So this line cuts the inner rim of this Smith chart, and this is the intersection point and crossing point. So this crossing point is the phase angle of the reflection coefficient. Phase angle of the reflection coefficient. Now what is the phase angle? And this is 50 degrees and this is 60 degrees, and approximately 54 degrees. At an angle of phase angle is 54 degrees. So therefore The reflection coefficient at the load is magnitude of the reflection coefficient and phase angle of the reflection coefficient. And what is the magnitude of the reflection coefficient? 0.425, and the phase angle of the reflection coefficient is 54 degrees or 54.5 degrees approximately. So this is the reflection coefficient value. Next, determine input impedance to the transmission line. So given that the length of the transmission line L is equal to 0.4 lambda. Now here this OP line is extended. That extended line is cut to the outer rim of the Smith chart. At that point P dash, the wavelength is 0.14 lambda. Adding this 0.174 lambda with 0.4 lambda, 0.4 lambda. So the load point P dash value is from this Smith chart 0.174 lambda. Adding this value with length of the transmission line, the length of the transmission line is 0.4 lambda. So adding these two values we get 0.574 lambda, 0.574 lambda. On the Smith chart, outer rim circle of the Smith chart. So observe identify 0.574 lambda, and this is 0.48, 0.49, and this is 0.5. 0.5 plus 0.74, 0.5 plus 0.74, 0.07, 0.08, so 0.074 approximately. So this is 0.074, and this point is 0.574 lambda approximately. This point is considered as point B dash. This point is considered as point B dash, and after that using connect B dash point and origin point using scale. Connect B dash and center point using scale. So this line cuts the VSWR circle. That crossing point or cutting point is considered as a point B. Point B. So at point B, find out the normalized input impedance. At point B, the constant R circle is approximately, and this is 0.4 and this is 0.5, and approximately 0.41. At point B, the constant R circle is 0.41 or 0.42 plus, and the reactance circle at point B approximately, and the reactance circle at point B approximately and the reactance circle at point B approximately 0.4 plus J 0.4. So this is the normalized input impedance. So from the Smith chart, at point Q, the normalized input impedance Z suffix in is equal 0.41 plus J 0.4. Next, calculate the input impedance. We know that the normalized input impedance is equal input impedance divided by characteristic impedance. From this equation, the input impedance is equal normalized input impedance, normalized input impedance, normalized input impedance into characteristic impedance. So from the Smith chart, the normalized input impedance value is 0.41 plus J 0.4 into characteristic impedance. So given that the characteristic impedance Z0 is equal 50 ohms, multiplying 50 within the bracket term 0.41 into 50, 20.5 plus J 0.4 into 50, 20. So this is the value of the input impedance of the transmission line.